Hey students, Professor Nugent here. In this video, we are going to discuss using ordinary least squares to estimate the coefficients of the multiple regression model that we introduced in the last video. With two regressors, as we discussed in the last video, the ordinary least estimator solves the following objective function. It is a minimization function. Right, we're minimizing something. We have yi minus beta naught plus beta 1 times x1i minus beta 2 times x2i. This is going to give us an estimate of y hat. And so we are in effect minimizing the sum of squared residuals. As before, the difference here that we have an additional regressor. Okay, we have this additional term, beta 2 times x2i, but we are still minimizing the average squared difference between the actual value of yi and the predicted value based on the estimated line. Okay, this minimization problem is solved using calculus. When we get into multiple regression, the solution is we want to use calculus and linear algebra. Calculus or linear algebra, rather. But it starts to get more complicated, so we leave that for graduate econometrics. And if you're interested in that, in the theory behind the tools that we're using, again, I invite you to take ECO321 with me in the fall. So this minimization problem, it gives us our ordinary least squares of beta naught and beta 1. We are minimizing the average squared difference between the actual values of yi and the prediction, which is the sum of squared residuals. Okay, folks. Let's look at the California test score data as an example. Originally, we had a regression of test score against the student-to-teacher ratio. You should be seeing hats here. PowerPoint has problems. Those are hats. The predicted value of test score in the univariate case is 698 minus 2.28 times the student-to-teacher ratio. If we include percent English learners in the district, the regression becomes predicted value of test score is equal to 686 minus 1.1 times the student-to-teacher ratio minus 0.65 times the percent of English learners. Observe that the coefficient on the student-to-teacher ratio gets smaller. And further note that the correlation between the student-to-teacher ratio and the percent of English learners is positive. So what you had is that in the univariate case, this variable was picking up more stuff than just the student-to-teacher ratio. You also had the confounding variable percent of English learners pushing that coefficient estimate higher because these things are positively correlated. So you had this confounding effect. This omitted variable bias was pushing the coefficient higher than it actually is. When we include the regression in the equation, the coefficient becomes smaller from 2.28 to 1.1. We get a more pure estimate of the effect of the student-to-teacher ratio on test score. And it seems like it's much smaller than we originally estimated. Let's look at how this plays out in Stata. We are still, this will always be reg y x1 x2 comma robust. Okay, that will always be our syntax. And in this case, y is the test score, x1 is the student to teacher ratio, x2 is the percent of English learners. We run the regression and we find the following coefficients. The test score, the student to teacher ratio, the coefficient on the student to teacher ratio is negative 1.1, as we saw in the last slide. Okay, the coefficient on the percent of English learners is about negative 0.65. Our intercept is about 686, and notice that these are all statistically significant. The intercept and the percent of English learners are statistically significant at 5%. The student to teacher ratio is significant at 5%. We can also claim that the percent of English learners and the intercept are statistically significant at 1%, because these p-values are smaller than 0.01, but the p-value for student to teacher ratio is larger than 0.01, so it is not significant at 1%, but it is still significant at 5%, because the p-value 0.011 is smaller than 0.05. And we will get into more detail on this printout